From classical heights to quantum energy levels, watch as we apply the WKB approximation to a seemingly simple problem. And here we see a bouncing ball done on an actual neutron that mimics this exact question. So, the task today is to analyze the bouncing ball using the WKB approximation. In part A, we want to find the allowed energy levels En in terms of m, g, and h bar. In part C, or part B, now put it into the particular values given in problem 9.6c, which were for m and g, and compare the WKB approximations to the first four energy levels with the exact results, which this is now posted on Patreon, so if you want to get the copy of it, feel free. In part C, about how large would the quantum number n have to be to give the ball an average height of, say, 1 meter above the ground. Now, this particular part will show you how vastly different the scales of the classical world is with the quantum world. So, why do we care? Clearly, we're trying to bridge the classical and quantum worlds, and hence this is known as the quasi or semi-classical approximation, which is actually kind of cool to see it come to fruition. But the challenge is, what are the limitations with this approximation method? And as always, the PDF is available, though I would say comment if you want it because there's weird linking going on in the captions. I still have not figured out why it's not like in Patreon, but we'll let that be where it is for now. But now on to the question, and let's dive in. So, stop number one. What we have to realize here is that for potential like gravitational potential, we have to analyze it as a potential well with one vertical wall. And if we're using x as the height that the ball is dropped at or reaches, then there's no such thing as negative height when we set our axes and reference points to 0. That will make this make sense. So we say that we put anything at 0 to infinity, and that's what exactly mimics the potential well with one vertical wall. So here, since our potential varies with height x, we just set it up here, and then we see that this line here, this linear line, mgx, is what we're working with. And then here on the v-axis, we have infinity at x equals 0. And so we just say for some arbitrary energy level E, eventually we run into what's called the turning point. Okay, and that's what x2 is highlighting there. Now, the turning point is by the book definition where E equals V, but if we consider this like a roller coaster, right, if we have some level of energy here that the roller coaster can roll up this ramp, eventually when it reaches this E level, the roller coaster can't exceed that, so then it starts to fall back down. And I can't remember where I saw the roller coaster analogy. Maybe it was in Marion and Thornton's. I can't remember, but there's a couple books in the classical mechanics worlds that help us find these turning points when we're doing phase diagrams. So I would say check those if you're more curious about how to find them. Otherwise, just stick to the math that V equals E is the turning point, and you'll be good to go. Now, the reason why we need this is because in the WKB approximation, the allowed energy levels En are found by solving the quantization condition, which is listed by equation 9.48. So it's quantized because we have some step level n, right? That n would be for 1, 2, 3, and so on. And here we have to couple this with equation 9.2, or the momentum that encompasses the En, and we have for some energy level n. So now what we have here is that V of x is equal to mgx, which is the gravitational potential. Cool, that's easy to work with, all things considered. X1 here is 0, and that's the point where the ball touches the ground, where the energy would also be 0, theoretically. And here we have x2 is equal to En over mg, the turning point where the kinetic energy becomes 0. But where did this come from? Let's take a quick look at that. So if we set the potential energy equal to the En, we see that we have mgx2, because now it's a turning point, equal to En, and so if we solve for x2, we get En over mg. So that's where we're good. And our task now is to determine the WKB quantization condition, starting with the integral. And so from that, we see that we could take out the constants 2m and the square root, and we're left with En minus mgx dx. Cool, so this does vary with position, and that's kind of cool to see. And if we let u equal the argument inside the square root, so En minus mgx, clearly solving for du and dx, we get this relationship where dx equals the minus of 1 over mg du. And now let's go ahead and tinker with the limits of integration. In doing so, we plug in the upper limit, so En mg, into the square root, and we get En minus mg times En over mg, so mg cancel, En cancel, so we get a nice 0. Love that for us. At 0, we see that we just get En, so this simplifies our life dramatically. And so if we plug everything in, we get upper limit, lower limit, and our du, our dx substitution. U just goes to the square root. Now we could switch the limits of integration, but that will come at the cost of a negative sign. So we do that here, and it simplifies our life even more. Taking the mg out front, putting this square root of u to the 1/2 power, and I highlight m here for a reason, and we're going to combine that with the m in the square root to make sure that we only have one singular m term, not more floating constants. So putting this m into the square root and taking the antiderivative, we see that we have to square the m, and that square can't, and that one of these factors from the square cancel with this m up top, so we're left with 1 over g out front. And then we see here that we add 1 to the power, so that gives us 3/2 power, and then we divide by the new power. Since we're dividing by a fraction, we multiply by the reciprocal, and that's why we see 2/3 over here, and g there now has some companionship. And now we see the square root simplifies to 2 over m, and we have u to 3/2 power. They need to be evaluated from En to 0. So not that bad of an integral, all things considered. So evaluating this, we get our En term here, our 0 term here, but zeros make our life easy. So we finally get our conclusion of the integral, which is 2 over 3g root 2 over m with En to 3/2 power. And if we apply the quantization condition, what we see is that we get n minus 1/4 pi h bar. So clearly, if we want to solve this for energy, we need to divide by all our constants, but the constants are fractions, so we're multiplying by reciprocals. Hence, we get 3g pi h bar over 2 with the square root of m over 2 because reciprocal, and then n minus 1/4. Now we got to get that power off of En. And so we square everything first, square, square. The reason we do this is because now we can simplify our coefficients and all the nice stuff here. So from there, we get rid of the square root that our m was on. So we get 9, 4, g squared, pi squared, h bar squared, as you probably would expect from something like this potential, a bunch of squares. Now we simplify down to something relatively nice. The 8 comes from 4 and 2. So we're good there. Now we're just left with e cubed, so we got to take a cubic root, and that's highlighted with the 1/3 power there. So we have successfully found what the En level is. And from this, we can see that we're going to have staggered lines to look at. What I mean by that is, for energy levels here, and based on how you notate in this book, it starts at n equals 1. Others can start at n equals 0. This is actually found from a Mathematica notebook, which I'll link below or try to. And it's pretty cool. You get to see how for this bouncing ball problem, we have the different energy levels. And we can see here that from 1 or 0 to 1, it jumps a lot. Then the jump kind of gets smaller and smaller and smaller. So what this tells me is that we're going to have a very large N to look at if we're trying to get something for 1 meter on the x-axis. So that's going to be something to look out for here soon. And since we have our turning points here, we can just graph it because that's En over mg. That is the turning point. So we can know that we're going to hit here and we get everything turned around. So that's pretty cool. But let's get on to part B. So part B wants us now to analyze it numerically and give a couple things. Here for G, we're supposed to use 9.8 meters per second squared, and M is equal to 0.1 kilograms. Cool. So if we plug everything in, before we plug everything in, let's realize that this energy level has the form of a coefficient. That's going to stay the same regardless of energy level. And so we have that to the 1/3 power. We split this up to the 1/3. And here we have something that is reliant on N. So because of that, we call this thing alpha, as indicated here. And we call this parentheses beta, as indicated here. And note that this is squared, this is 1/3, so we get a 2/3 power. This will save us time later, trust me, but making sure that we solve for the coefficient by plugging in these constants, we get our mass term, gravity, Planck's constants, and joules times second, so joule second. And then after that, we see things cancel out nicely, and we get 1.05877 times 10 to the negative 22 joules. That is incredibly small. So just keep in mind that if that's so small there, that's going to highlight how big of an N we're going to have for part C. So let's compare this with the exact energies. As we see here, we have a column for N. So that's 1, 2, 3, 4. And betas turn to the 3/4, 7/4, 11, and 15th that we need to take the 2/3 power of. So multiplying our alpha with our beta to the 2/3, we get 10 to the negative 22 or 23, 1.5, negative 22, negative 22, negative 22, all very small. Now, in the exact energies, where we had to solve it using the Aries functions and a differential equation, that was a lot more hectic. And again, it's available on Patreon now, so if you want that PDF, feel free to go grab it. But it's actually a pretty cool process what we did to find the exacts. That being said, the exacts were a lot of work. So far, this problem is not that much work. But as we see, 2.55, 2.55, 2.07, 2.07, 1.53, 1.53, 8.73, 8.80. So outside of the n equal 1 case, all of these are the same within 3 significant figures. That's pretty darn good in my opinion. So, you tell me, if our situation is not that dependent on mass per se, and we can just have one highly valued constant of mass, then the approximation here seems to be worked out pretty darn well, right? So I would say that you're going to win big time with this approximation. But as we see here, using that same diagram from the Mathematica notebook, here's what the wave function would look like in this bouncing balls spectrum that we have. And if you actually read the paper by Green, where they highlight that picture that we saw in the opening, we saw that we had dealt with wave functions. These are the same style of wave function that we see. We get multiple oscillations in each energy level. So that's pretty darn cool to see come through, especially on a computational sense. So go check out those papers. They're really fun and highlight that this problem is not as arbitrary as it seems or artificial as the author indicated in the problem statement. All right, so now on to part C. The results we found in problem 9.6 part D was that the average height, which is noted by the expectation value for x, thanks to Viral's theorem and a couple other things, was 2 times En over 3 mg. So if we plug in the En that we found from our problem here, we get this nice bracket with the 1/3 power. But as we saw in the substitution, we had the alpha with n minus 1/4 to the 2/3. Now, I told you doing that alpha early would save us time, and here's the proof of that. So we have 2 alpha over 3 mg, uh, and then we have n minus 1/4 to the 2/3 power. But this problem's asking us to solve for what n would lead us to have a height average of 1. So now we have to solve this for n. So naturally, we have to push all those constants over. So divide by a fraction or multiply by the reciprocal, you get the same thing. So 3 mg up top, you get 2 alpha up below. Now, in order to uncover this n, we have to multiply by 3/2 power on both sides, or raise everything to 3/2 power on both sides so that we get a cancel of powers on the n term. And then now from there, we just add this 1/4 over. So what we're given is n equals this bracket to the 3/2 power plus 1/4, from which we go ahead and plug in all our constants, m, g, the average height that we want, with the alpha term that we solved for earlier, 3/2 power, again, use a computer or Mathematica, and then of course the 1/4, which is seemingly not going to do anything. And as I promised, we got a very large n, 1.63596 to the 10 to the 33. Now, if this does not highlight how vastly different the quantum world is from the classical world, 1 meter means nothing to us in the physical world, or the classical world where we have, and we can just bounce a ball. That's pretty easy. But the fact that you need an energy level that high for n tells us the scales are completely different, and trying to warp our brains around this is a fascinating exploration. And same can be said when you study astrophysics. When you're talking about scales as big as what we see in light years, that too hurts my brain. And putting these two things together has been quite a challenge for physics as a whole. So seeing numbers like this definitely highlight how different all of the regimes are. So that was a fun problem though. Holy. Well, thank you for listening. That was a fun problem that I thought was definitely artificial, and then thankfully the book links to several papers that proved otherwise. I have those papers as PDFs. I downloaded them. So if you're interested in that, please reach out so that you can have a copy of them because I thought they were really darn cool. In summary, though, I think we see here that applying this method is a lot more about how you set up the system than the actual mathematics of it. Because without proper setup or knowing that you could use a gravitational potential as a one-sided well, that might look that might send you into a different regime. And so the setup here is very important. Again, dealing with the Aries functions, which you could see in the Patreon PDF, that was fun, but it's still not covering a full host of the Aries functions, which I guess with the Bessel functions of 1/3 order might come later in a kind of more uh, elaborate upper level book. But still, it's good to be exposed to all the concepts. So thank you again to all the supporters of the channel. You make this possible. And if you want, you can also support this channel by, liking, subscribing, sharing with a friend, joining the Patreon, especially with the new semester rolling in, or donating through Buy Me a Coffee where no account is required. Of course, books, notes, and other reference materials are found below. If you have any questions, please feel free to reach out. This is about fun and learning and exploring. It should be a mental workout, but at least now you can see different ways of approaching problems. This book has been done, taught in so many schools that I'm sure there's other styles of solutions too. Please feel free to explore them all. This is for you to gain insight and for us to have fun and talk about how weird this world is. So, with that, stay curious, keep learning, and until next time, have fun in the process because that's what is going to keep you in the process. See you later.